can see that everything kind of arranges itself around the L2 cache. L2 cache is kind of new in Fermi. Previous chips haven't had a two-level cache. They haven't even necessarily, they've had lots of specialized L1 caches. So you'd have specialized texture cache, specialized instruction cache, address fetch caches, things like that. But Fermi really generalizes the caches. And there are still some specialized caches, but Fermi generalizes it. We also have a much more unified memory architecture. And I can talk about that more later. But what you saw for the GT200 system, GF100, which is the first Fermi, and all Fermis after that, will essentially have a similar layout, but much more so. So going from, shoot, I don't even know how many cores GT200 has, but Fermi has 512 processing cores in it. These can operate fairly independently. So before, well, I'll talk a little bit about it in a bit, but a lot of transistors, 3 billion, that means a big die. Big die means lots of difficulties making it, but it's a powerful chip with a lot of arithmetic units in it. By the way, pretty much all of that green that you see up there is math. All the rest of it is not math, but if you look at it as a proportion of the chip, this is a huge amount of math. I mean, this is, call it 50%, maybe 60%. On a CPU, you're going to see something about like that, 20 to 30% math. That's one of the reasons that we can blow them away in terms of parallel processing is we just have a lot more math resources to throw it at. The thing that we sacrifice, we don't have anywhere near as much branch prediction in the hardware, control flow stuff, we just don't have it, but we don't need as much. And also, as you can see, we're getting to have more of that stuff than we used to, and we have a little bit less math than we used to. So kind of the takeaway is that GPUs are getting more CPU-like, and CPUs are slowly getting more GPU-like with Larrabee. So. Oh, yeah, one thing I'll toss out when we talk about CUDA a little bit later. CUDA is traditionally C. You can write a C program with some specialized extensions, and without a lot of extra work on your part, you can have that C program partitioned into a GPU part and a CPU part, and it just runs where it's supposed to, essentially. Fermi is written in such a way that now you can use C++ with it and do, well, I won't get into the benefits of C versus C++, but for those of you who like C++ and feel that it's worth using, Fermi is very nice for that. So for a streaming microprocessor inside Fermi, this is kind of how things are laid out now. Instruction level cache, register files, specialized computation units, and then more cache down below. The interesting thing is the scheduler and the dispatch, there's a lot more logic in each particular streaming multiprocessor now about scheduling and dispatching so that we can actually do much more sophisticated things than previous hardware could do. So, we talked earlier about how things all started out very specialized fixed functionality. Now we've moved very far away from fixed functionality, where each computational cluster or stream, SM if you will. I'm just going to call it SM for now because it's a smaller thing to say. But each SM has a lot more flexibility in it about what it can do. And this is actually kind of suggesting that it can do multiple things at once, and that's sort of true. These cores no longer work in lockstep. They're not completely independent, but they're no longer in lockstep. And when we get on to CUDA, we'll talk about threads, warps, and blocks. But it's basically a way of specifying how the parallelism works in a very flexible way. The last thing I'll mention on this slide that's probably worth talking about for this is the configurable cache and shared memory. When you write a compute program, you can either have all of the threads in one particular block of computation having a shared memory that they can all access together, regardless of how you schedule the synchronization between the threads. They can all reference this block of shared memory, which is very fast and useful for some applications, not so much for some others. And so traditionally, what we had was a 16K block of shared memory that all these things could use, and that was it. Now today, it's split between an L1 cache and shared memory. So if you're working on the sort of thing that's going to do a lot of memory accesses that are unpredictable, you can now use cache here instead of shared memory, and we actually give the programmer the ability to specify whether they're more likely to need and want shared memory or more likely to need and want cache, and we can actually change the configuration of the cache and the shared memory so that they can get better performance out of this. And if you're interested in that, I can go on a little bit more about that later.
I do have a question. Can you talk about the size of the register file for each of these SNs?
Oh boy. You know, I don't remember what it is. I want to say it's 16K, but I don't know why I think it's that number.
But considerably larger than a standard CPU.
Yes, because we have all these cores to work with, you do need more space than you would on a CPU. I mean, I don't know that it scales exactly with cores, but it does scale. So yeah, just a little more Fermi evangelism. One of the things that's become really important with general purpose computing is floating point. You know, for graphics, you don't really need floating point that much traditionally. You know, you've got a 32-bit int that stores 4 8-bit components, and that's good enough for most people. Now, some graphics programs are more complex now, and they're starting to use floats, but you don't really need to be precise for graphics. You just need to be good enough so that you don't see weird cracking and edge effects and stuff like that. If, however, you're working on protein folding, or oil and gas discovery, or you know, medical applications, precision becomes more important. And single precision floating point with a 32-bit float also is not good enough. So one of the things that people who are doing heavy computation really need is double floats, 64-bit floats, that are fast and efficient. And so there's been a huge amount of work done throughout the industry, and especially at NVIDIA, as general purpose computing has become more important, float performance has become really important. So, you know, kind of, you can see that in each one of these cores, we've got a large chunk of logic for both floating point and integer logic. And you know, we can do 64-bit integer logic, and some people care about that, but really 64-bit is all about double precision. And that's really important for a lot of things. And you used to have to do a lot of contortions to be able to try and get something resembling double performance in your shaders or in your CUDA stuff, and now that's not nearly as much of an issue. And it used to be that when you got it, it was slow. And that's been one of the focuses in the industry, is that now when you get it, it's fast. It's not as fast, but it's pretty close. Yeah, lastly, this is one thing that we've talked a little bit about, but I haven't really talked about how CUDA exactly works, but for now we can say that the lowest level primitive in CUDA is a thread. Threads are grouped together in blocks of threads, and those blocks together are grouped from a kernel. And a kernel is some chunk of code that you want to run on some chunk of data or some collection of data. And you know that this kernel is basically all doing the same thing, but for performance reasons, you're going to chunk it up into smaller pieces of work, and so you're going to say that each block is 32 threads or 100 threads, and these 100 threads are all going to be doing about the same kind of thing. And it used to be that each kernel had to run pretty much alone on the GPU. So if you had a kernel that wasn't really doing all that much, you had a lot of wasted time, a lot of wasted power on that GPU. So one of the things that we've been working really hard on is concurrency, so that instead of having all of those cores lockstep working on the same basic programmable kernel,